well, get the party started, as it were, our Tuesday afternoon party sessions. So we have the course website here. No updates that I know of. Just a reminder that homework one was not due yesterday anymore. It's pushed until Thursday. So you've got a couple more days to work on that. Are there any questions on homework one that I can help you with? No one wants to be brave right now. That's okay. If you do get stuck, sending me screenshots of the error message and your syntax will help me try to get you unstuck. I'm happy to do that. And if you have problems getting the numbers to turn green, please let me know about that as well. Otherwise, it'll be due Thursday night, and hopefully, if everybody gets it finished, then we'll be able to go over the answers on the next class. Otherwise, we'll have to wait. All right. Can everybody hear me okay? Yes, okay. I was trying to play with my mic so that it didn't catch my breathing quite so loudly. I've noticed that on the videos. I sound like one of those like creepy, like heavy breather people. I don't intend to do that. It's low production quality for the class, right? It's a free YouTube channel, so I'm not beholden to make it fancy. And no, I don't actually have any merch, in case any of you were curious. That's what the kids say in their YouTube channels. It's always about getting the merch. Um, All right. So what are we talking about lately besides merch and how nice it is outside? What did we start talking about last week? What do you remember? T-tests. Yeah, we started talking about T-test for significance. So we started doing that with respect to testing sample means against population means. T-tests are also used to assess the significance of Pearson's R. Bivariate, yep. So we've moved from just talking about one variable at a time to talking about two or more variables at a time. Two variables this week, more variables coming soon. What about Pearson's R? What do you remember? As x goes up, y goes up. Yes, so if that is true, it's named after a white guy. Also true. Yes, dead white guy in this case. Pearson's correlation dates back to the 1800s, I believe. If x goes up, y goes up, that's a positive correlation. Yes, and the most positive it can be is 1. And if x goes up and y goes down, what kind is that? Yeah, negative. So, and the strongest negative correlation you can have is -1. So the number that goes with it is the magnitude of the size of the relationship. The direction tells you which way it goes. As x goes up, y goes up. As x goes down, y goes down. If they agree, that's a positive relationship. If they disagree, that's a negative relationship. Great. What about linear and nonlinear transformations? Ring a bell? There's one in particular that I want you to remember, which is z-scoring. That one is a transformation that changes the scale of a variable so that it has a mean of 0 and a standard deviation of 1. So standardizing puts it into a different metric. The one that is almost always used is the z metric of mean 0, variance 1. The other things folks are contributing that we remember, yes, t of 2-ish is normally your cutoff. So yes, the process of significance testing, I've had some questions over email and in meetings with students, so I think that's probably a good thing for us to review. Other topics that you want to review today before we jump into new stuff. So we'll talk about T and significance testing. Anything else you can think of? I'm eagerly waiting the chat window.
Can you please repeat? Then you talk about the strength of it so being something and the correlation of how close it is something else. Can you please repeat that?
Sure. So a correlation of 0 means two variables are unrelated to each other. The further away from 0 the correlation is in absolute value is an indicator of the strength of the association. So -1 or +1 are equally strong correlations. That's the highest you can have. The difference is in the type of association that those numbers convey. So a positive correlation conveys a match as x goes up, y goes up, or as x goes down, y goes down. A negative correlation conveys a mismatch where one goes up as the other goes down. Okay, does that help?
Yes, thank you.
Great. All right. Other things then, we were talking about Pearson's correlation. Pictures that go with that. So just going to flip through a couple slides here as a way of reviewing. Can you all see my screen, by the way? Make sure that's working. Okay. Thank you for the emphatic nods. I appreciate that as well. So we have pictures here illustrating the different kinds of correlation where you just have like a sphere of balls. In the middle would be 0, and then they form more of a line in either, I'm trying to get it right for you guys. This is negative, and this is positive since it's mirror image for me. And each of these correlations can be tested for significance using T, our new best friend. So in general, steps in significance testing, let's stop at this slide 15 to do a review. Maybe, come back, there we go. All right, so anytime that we want to make some sort of decision about a sample statistic, like a correlation, relative to some expected benchmark. So that's the null hypothesis. What do you expect to find? And it's not necessarily what you want to find, but it's your basis for making some sort of inference. Almost always when we're talking about correlations in a sample, we're comparing to a null hypothesis of no correlation. That's usually what people are going to put as their benchmark. That way they don't have to weigh in advance as to exactly what the correlation would be. Now, you might have a research question or a research hypothesis that says, I think these two variables are going to be positively related, or I think they're going to be negatively related. But in terms of the test that we do, it's almost always against a null hypothesis of 0. So in deciding what kind of test is appropriate, basically you want to set ahead of time your alpha level. So that is, how often are you willing to be wrong by chance, basically. We're going to introduce the terms either later today or next time of false positive and false negative. An alpha is the proportion of times that you would have a false positive. So I have no relationship for real in the population. What percentage of the time would I find one that's declared significant just by expected normal fluctuation of samples? So traditionally, we set an alpha of where unexpected is of 5%. If you're willing to say that unexpected could be because it's either positive or negative, so too high or too low relative to your benchmark, that's a two-tailed test. And that's usually the most appropriate case. So the role of T is to standardize the sampling distribution of your statistic, to put it in terms of the null hypothesis as the center, and the width of the sampling distribution is given by a standard error. That's what T is for. So it's no matter what kind of data you have, it's trying to place it into a space where you know what the numbers mean. And a T value of 2-ish is generally consistent with an alpha level of 0.05. So when you do these tests, such as a Pearson correlation, you will get a p-value. You won't always get the t statistic that goes with it. Sometimes you will and sometimes you won't, but you will always get a p-value. And the p-value tells you the probability of finding what you found, something more extreme than what you found, if the null hypothesis is true. So in reference to that set of expectation that's your grounding point, such as a correlation of 0, where does your correlation fall? And if it's far enough away to where it would be expected less than 5% of the time given normal sampling fluctuation, it is declared significant. And so the word significant goes with reject the null hypothesis, would be unexpected. The opposite of that is it's well within expected territory. We retain the null hypothesis. It is non-significant.
Hey, when you use the term positively related or negatively related, you're referring We're referring to the Pearson correlation.
Mhm.
Okay,
Yep.
great.
In 2 weeks, it's going to become a slope more generally. But yes, an association that is positive, they both go up. An association that's negative, one goes up, one goes down.
Okay.
Yep, good question. Okay, so other questions or parts of that that you need to hear again or hear differently. Okay, so then in the case of Pearson, once we know the Pearson R, there's only one other thing that we need to know in order to get our t-test statistic. So unlike the test of a sample mean against a population mean, we don't need a standard error to get to t. Standard error turns out to be a bit more complicated than that, and we'll talk about that today. But the only other thing that's in this formula, can you see what I have highlighted on slide 16? What is in that formula besides R? What other letter?
Capital N.
Capital N. What's capital N in our world?
It's the number of the sample.
Sample size, yeah,
Yeah.
number of people.
Number of people in the sample.
Yep. So for the same R, the more people you have, the more T you have. It's easier to find a test statistic that heads into unexpected territory the more people you have. So this is setting up an important distinction between just testing for significance and paying attention to effect size. And that is the article that I gave you for this week. The Earth is round, p less than 0.05. Gesundheit. Fall allergies are the worst. I feel like my nose is on fire after I've been outside for a while. But the biggest criticism of significance testing in the way that we're describing it is that it's too easy to say, oh, p less than 0.05, it's significant, and not pay attention to just how large of an effect you actually have, just how strong of a correlation you have. If you have enough people, you could find a correlation of 0.1 to be significant, to be sufficiently unexpected if the null hypothesis of zero correlation were true. Now, would you get super excited about a correlation of 0.1? It's not very big. I mean, there is a positive association, but it's more noise than signal at that point. It could be declared significant if you have enough people. So we don't want to pay attention to just whether or not we're rejecting the null hypothesis, calling something significant because it would be sufficiently unexpected. We also want to pay attention to just how strong the association is. And Pearson R gives us a ready-made version of that. How strong the association is known as effect size, and Pearson's R is a very common effect size. That correlation metric of -1 to 1 is used in a lot of different instances. So in this example that we were looking at, the correlation turned out to be 0.99, which is about as good as you can get. And so unsurprisingly, it's significant. So our t-value is around 25, means that we would expect a correlation that strong if the true correlation in the population were zero, less than 0.0000000% of the time. So less than 0.0001 is the level of precision that your software will report it to. All right, so we talked about that. We talked about adjusted R, and so that corrects the Pearson estimate of the effect size for smaller samples. So it's going to bring it down in those cases of small samples. And let's pick up here. I think this is new. So slide 18. So a little bit more about R and describing R and its expected variability across samples. So the process of testing a correlation is different than a lot of other things that one does in statistics in terms of the sequence. So when we were talking about, say, comparing a sample mean to a population mean, we need to know three things to be able to do that. We need to know what the sample mean was. We need to know what the expected population mean would be. So that comes from previous literature or some sort of known standard. You would not bother to do that test unless you had some known standard. I gave you some made up numbers to play with in your homework, but those wouldn't be helpful in real life. And once you know the sample size and the standard deviation, you get your magical quantity, the standard error. And that's the thing that allows you to create your t. In looking at Pearson's correlation here, we haven't talked about standard error for Pearson's correlation yet because we don't need it. You can go straight from the R effect size that captures both the strength of the relationship and the direction, and go straight from that to T. The only extra thing you need is sample size. So as I just pointed out here, the more people you have, the easier it is for you to say that any R happens to be significant. So you want to pay attention to both the strength of the R, the effect size, certainly the direction of the R, which tells you the pattern of the association, and the significance. Significance is largely a function of sample size in this case. So how do we talk about expected inconsistency, right? If I have an R of 0.3 from my one sample, is that 0.3 is my correlation, or is it like 0.3? Right? It's the same problem with the mean. The fewer people we have, the less faith we would generally have that any one sample is going to give us a right enough answer. Trying to figure out how, I'm going to go with this word again, wiggly. Can I stick with wiggly? This is the gesture for wiggly. Yeah, how noisy, how inconsistent across repeated samples your correlation would be. Trying to figure that out is a little bit more complicated in the case of the correlation because the correlation itself is bounded. It can be only -1 to 1, and it can't go outside those boundaries. And so making sure that we can compute ranges of wiggliness that stay within those intervals is a bit tricky. But fortunately, people smarter than me have already figured out how to do this, and fortunately, it's programmed into statistical software. So one more line of code and you can get this too. So we talked about confidence intervals in the context of means. So confidence intervals to describe the, I'd say, expected wiggliness around the mean. That's sort of a colloquial term. More generally, it's the proportion of samples in which the population version of that statistic would be found. So if you're talking about means, it's relative to a population mean. If we're talking about Pearson correlations, it's relative to the population version of the correlation, the right answer. And we typically assume we have a symmetric interval where the middle of it is the estimate. And the critical value refers to what distribution you're using to approximate the sampling distribution. It's going to be t in most cases. And the standard error gives you the width. But we don't have a standard error yet. So let me show you how to get one and why we can't just get one in the original R metric. So this is another simulation example. I made up fake data because fake people are very well behaved, as it turns out. They do exactly what you tell them to. So I simulated two bivariate normal distributions, meaning two variables that each have a normal distribution, so that's sort of like bell-shaped hump, and one of them I set so that the two variables have a correlation of 0, and in the other, the correlation is 0.8. So question, what was the definition of the standard error within this CI context? It's a standard error that refers to how variable the correlation would be across samples. And I haven't shown you how that's computed yet because it actually requires a few extra steps relative to what the standard error was for the mean. So that's where I'm heading, is how do we get a standard error? So in the first row here is if I take my population of 100,000 fake people and I draw a sample of 10 people, I compute the correlation. Send 10 people again, correlation. 10 people again, and I do that 1,000 times. Or if I choose 50 people out of my population or 90 people, this is what the distribution of the correlation would look like across samples. So with 10 people, it's supposed to be 0, which is in the middle here as one would expect, but it could be anything. With only 10 people, like any one sample of 10 people is not guaranteed to give you the right answer. This is a lot of noise that's happening right in here. 50 people, it starts to get a little tighter around the right answer, and with 90 people, it gets even tighter. So because the right answer, the population correlation, is 0, these sampling distributions around that 0 point are symmetric. And if I compute the average correlation that I get across my 10 people, my 50 people, my 90 people, it's right around 0 like it's supposed to be. The difference is in how noisy it is across samples, how much wiggle it is. So this last column right here, this is like the standard error. It's how far off any one sample's correlation is going to be from the population correlation. So I know what it is because I made up the data, and it's a lot higher for a sample of 10 people than a sample of 90 people. But what happens if I have a correlation that's really strong? So in the bottom part of this panel is when the right answer is 0.8. Same problem, the fewer the people, the more likely we are to be off of 0.8 in any one sample. The correlation is a lot noisier, wigglier, more likely to vary around where it's supposed to be. The more people we get, the tighter that range gets, but it's going to bunch up against 1. So if I tried to form a confidence interval, look at what's going to happen if I use this standard deviation of how the sample correlation varies across samples as my standard error. Well, if the mean is 0.77 and I want to go 2 standard errors around that, what's going to happen? What's the high end of my confidence interval going to be if I use these numbers? 0.77 plus 2 times 0.15, that's over 1. And I told you like 10 minutes ago that it can't go over 1, right? So there's a logical inconsistency here. This is known more generally in statistics as a boundary problem. And whenever you're trying to create a standard error for or a confidence interval for a statistic that can't go past a certain point, those intervals cannot possibly be symmetric. So we have to come up with a workaround. We have to transfer this bounded interval that is locked between -1 and 1 into an unbounded space that we can use to compute standard errors and confidence intervals. And that is an example of a nonlinear transformation. And it is yet a third definition of Z. I don't know why. Everybody likes Z. So this is yet another one. But this idea is trying to take your Pearson correlation that's bounded between -1 and 1 and stretch it into some metric that's unbounded. And this equation right here that uses a logarithm, that translates that gray line right here. So on the x-axis of this plot is the correlation coefficient in its original metric of -1 to 1. The yellow line is the corresponding range of this thing that's called the Fisher Z transformation. Fisher, yet another dead white guy, naming things after himself, by the way. And as R gets closer and closer to the boundaries, this Z value just keeps going on and on and on. So it's placing R onto a metric that is unbounded on both sides. It's close to what's going to be known as a logistic transformation later on in statistics, but not quite. But the idea is that we can't compute confidence intervals and standard errors on a metric that's bounded because we're going to run out of room. But we can do it on this metric and then back translate into the R metric that's bounded. So the way it works then is that we compute the z version of our correlation. We then can get a standard error for it. That's a function of sample size. We can use that standard error in the z metric to compute a confidence interval in that unbounded yellow metric. And then this equation right here back translates z into r. And this is the kind of thing that I used to have to do by hand. I know, right? And it was actually fairly recently that I realized that I bet software can do this by now, right? I'm sure this is a thing. And yes, it is a thing. So I will teach you how to get confidence intervals for your correlations in addition to just the R value and the point estimate, or the point estimate and the p-value, I should say, because it's important to provide your readers with some sense of just how precise your correlation estimate is. I mean, they can sort of intuit, well, they only have 20 people, it can't be that precise, but okay, how unprecise is it? Right? If I tell you that my result says I have a correlation of 0.5, p less than 0.05, I win. I have a correlation of 0.5. I found what I was looking for, yay me. But the confidence interval around that is like zero point 0.1 to 0.9. It's like, okay, that could have been anything, right? You got lucky. Versus I say it's 0.5 and the range around that is 0.4 to 0.6. Okay, well, that's much more precise. That's much more informative. So we want to give our readers a sense of the wiggliness of our sample statistics. That's going to be a function of sample size. Okay, how are we doing? We're not doing. That was a long pause and some very tentative thumbs ups. So the big picture here, what are we trying to do? We're trying to see whether or not two variables are related. How we do that depends on what kind of variables they are. Right now, we're talking about the specific case where we have two variables that are each quantitative. And Pearson correlation is one way to index their association in a linear form, ... If they have a different type of relationship, then this won't be a good strategy. And just like any measure of association, we want to know just how strong it is, and we also want to have some way of extrapolating to the population where it came from. How likely would we be to find a correlation this big if there really were no association at all? The p-value gives us that probability of observing a correlation this big. The correlation value itself tells you how big it is, how substantial, there we go, the association is. And the confidence interval around the correlation helps to give you a sense of, if I repeated this study over and over again, like what range would this fall in? Like how precise is this? What the confidence intervals are supposed to help convey is this idea right here. Like if I were to take samples of the same size from the same population, how precise, how inconsistent would my correlation estimate be? So conveying that imprecision is just as important as conveying the estimate from any one sample. Does that help a little? Maybe? Okay. Do you want to see how to do it? Would that help? All right, let's see how to do it. Because knowledge is power. All right, I'm flipping to example 2. So this is another handout that goes with this unit, where I'm going to walk through syntax and output in each of the programs and get you used to being able to generate these sorts of results using your own data. Does everybody have this? Ready? Okay. So the original files for this are also available online on the course webpage in a zip folder. This is me trying to pull stuff out so that I can talk about it. And hopefully most of what I'm going to say is already included here in comments. but feel free to ask questions as we go through this. It's just like a practical version of what we've been talking about using data. The data we're going to play with is the same data from example 1. So it's excerpted from the General Social Survey of 2012 that came with the Mitchell Stata textbook. So these are real people, but I don't know a whole lot about the study other than what the documentation that was included. So we're just going to play with a couple of variables and look at ways of measuring associations. So first step in either program, tell it where your stuff is. And I have helped a number of you troubleshoot this process. This is harder than the rest of the class, right? Like getting SAS or Stata to find your folder. I had no idea when I first started using the system that that would be the hardest part, but it is. So if you've already crossed that hump, you've already figured out how to get SAS or Stata to read in your data, you are home free. Everything else is easier than that. I promise you. So in SAS, telling it where your stuff is using this process. So I'm defining an abbreviation called file save, and it has as its referent, this is my folder. So this is my file structure. You'll note that I don't have any spaces in it because spaces sometimes makes the programs get mad. So I'm just in the habit of not putting spaces in my folder names. When you put in yours, if you are using someplace outside the H drive, you'll need to have this little piece in front, //client/. And the way to make sure that you get the right path is to use the Windows Explorer inside the virtual desktop, because when you navigate to your folder from inside the virtual desktop, it adds that appropriate prefix for you. So then proc import puts together the place that file save refers to. So when you see this combination right here, the ampersand, the word file save and period, that is then invoking the reference. So SAS is going to read that and go, oh, what did she say file save was? Come back up here, grab that, and put it in there for you. So it's like a find and replace kind of idea. And then after the slash is the name of the data set. And in this case, it's an Excel format. So I put the extension. I tell it what type of file it is. So dbms equals XLSX in this case. Out tells me where it's going to go in SAS. So it's going into my work temporary directory, and I'm calling it example 2. So I had several questions from folks about this idea of putting things in work. So work is a temporary place, and I'm guessing many of you have already figured this out, that when you come back to SAS, your stuff is not there anymore. But that's okay, because you have the syntax file, and all you have to do is run it again, and everything pops back to where it was. It is possible to work within what are known as permanent libraries in SAS, meaning that rather than send stuff to the temporary directory, you define one of your existing folders as a permanent place and you work with the data as it's stored on your hard drive. You can do that. However, this is my however finger, right? You know, when this comes out, you got to take me seriously. However, you can accidentally erase your data that way. Because when you make data transformations in SAS, it happens it happens like right then. It's not like if you screw up something in Stata or SPSS and you close the data and it's like, did you want to save this before you close it? And if you say no, then it's like, okay, like that's like a back door that you can get out of. There's no such thing in SAS. So if you were to do something to your data set to erase some part of the information or otherwise mess it up, you will mess up the one that's on your hard drive. Ask me how I know this. So I don't want you to learn that unfortunate lesson. So what we're going to do in this class is read in data from the safe place into the working directory. And you can screw it up as many times as you want because it's just a temporary directory and the safe place has the data in its original form. Now, if you go through this process and you're happy with the results and you want to save it as a permanent SAS data set, you can certainly do that, and I can give you the code to do that, but it's not strictly necessary. If you have the code that you've been typing into and you have the original data set in its original format, that's all that you need. You don't have to save the results. You just have to save the process that generated the results, which is the syntax file. Okay. And then the sheet name is an Excel thing that goes in here. If there's more than one sheet, you have that. And get names gives you the first row as the variable names in the data set. So any questions on data handling in SAS?
Yeah, I have a quick question, Lisa.
Sure.
So when we run all of our code, for lack of a better word, do we have to submit that, or really are we just using that to find the answers to the homework?
I don't need to see it, if that's what you mean by submit it.
Yeah. Yeah.
Because if you get the right answers, then I know that you have generated code that is sufficiently correct.
Okay.
There's more than one way to do everything. So if you found one of those ways and you got the right answer, then that's correct. Why this is helpful for you, I'd say there's two reasons to make sure that you are saving your process. So not just like writing over it. Like each time you do something, you want to make a new version of it. One is for reproducibility. That's a buzzword. Have you guys been inundated with that buzzword? Not yet? Okay, it's coming. It's coming. Reproducibility is like the new thing, except it's not new. It just means that you should be able to recreate whatever you've done down the road, or somebody else should be able to. And if you have a listing of all of the stuff that you did, that helps with reproducibility. And if you're looking at a project and you come back 6 months later, you may not remember what you've tried. You may not remember which data file that you're using because once you get into these projects, you'll end up with what I call file hell, where there's like final version 7 as the name of something, right? And having all of the process as part of the code helps make sure that you can remember which data set you used, especially if you give yourself notes, I did this on this day for this purpose, that kind of thing. And the other reason to do it is that all of the stuff that we're going to do and all the stuff you're going to do like in the future is the same, right? Every time you want to get means of your variables, right? You don't want to have to re-find like the right way to do that. You'll open your previous work and like, when was the last time that I asked for means? Oh, here's an example of proc means, copy, paste, change. So you're building yourself a library of commands that you can then take with you, and that will help save you time down the road. Does that help? Maybe. Okay. Where was I? Oh yeah. SAS is not case or space sensitive. The only exception to that is things that are in this purple color. So you need to get the names of your stuff exactly right, including spaces or special characters or any of that kind of stuff. The other thing is that note that this is all one command right here. There's only one semicolon at the end of it, whereas these second parts here are each subcommands with their own semicolons. When I write code, I try to make it so that each statement is on a different line with its own semicolon, and I'll try to point out exceptions to that. But like right here, for instance, proc format, which is how you provide labels for the values of your categorical variables. Each of these is one command. So that's one set of label for a variable that's going to be called Mary. This one is indented right here because it's all one thing. So you can use tabs and spaces to make your code organized as to how to keep things segmented together. You don't have to do that, but it makes it easier to read and follow if you do. So this then is the process of labeling information. These are all labels for the categorical variables values that we're going to be playing with. So value, and then the name of the labeling convention. These all start with F because F stands for format in the way that I name things. And then it tells you what the numbers mean. And note that I have repeated the numbers inside each of these because that way they stay in the same order. If I didn't do it, it switches to an alphabetic order, which may not be the same, and that will drive me nuts. Then I'm adding the labeling information. So in all of your homework, I'm going to do this part for you, give you the labels of the variables. That way you'll have the names at the ready. So in this right here, this thing right here is an example of save as itself in SAS. I'm going into a data set, adding stuff to it, and saving it under the same name. So set is where the data are coming from. Data is where they're going to. Whenever you see the same name on both of these places, it's as a save as itself. Then I'm adding labels, where the name of the column is right here before the equal sign, and the label that goes with it to give it more explanation is in the quotes. Then I'm adding the formats from above. So the name of the column and then the name of the labeling convention that I want to apply to it. I'm going to be demonstrating z-scoring. So I'm making a copy of a variable that's going to be z-scored next. So in general, when we make new variables, you're going to start to see more examples of this. The new variable is on the left-hand side of the equals, and the old variable or the transformation of it is on the right. So what this little line of code is doing right here is creating a new variable called income z as a copy of the old variable that's called income. That way I'll be able to retain both the z-scored version and the original version in separate columns of the same data set. Likewise, this line right here is making another new variable to illustrate the effects of a nonlinear transformation. So income log is the name of the new column that's being created. And the way that is being created is from the original column called income, but applying a function to it. So functions, like this one, this is a natural log function, are mathematical operations that SAS has built in. So you can, for instance, take the mean across a series of variables, you can take the sum, you can find the minimum, you can find the maximum, you can find the standard deviation, you can find the natural log. So there's all kinds of transformation functions that are built in that it knows what they are. And log is the one we're using here. And then last but not least, proc standard is a way that you can do linear transformations on variables, such as z-scoring. And proc standard wants to know, okay, what data set do you want to use going in? And then it gives you the option of saving it as a different one if you want. That's the out statement. I'm going to keep it in the same data set though. And all of the variables on this list are going to have a new version created in which there's a mean of 0 and a standard deviation of 1. So this is a linear transformation applied to income, simply changing the scale for demonstration purposes throughout this example. And after you run all this stuff, it will be ready to use. Okay, questions on any of that? All right, Stata folks, I didn't forget about you. You get the next page. So very similar set of ideas, slightly different code to accomplish them. These two slashes here, these are comments. You can start with an asterisk or the slashes. I'm using the slashes to help to differentiate the Stata code from the SAS code as much as possible. Global file save is the same idea of defining the location of your folder. Make sure that it goes inside the quotes. No quotes in SAS, but there are quotes on this statement in Stata. If you already have data open, you need to get rid of it. Otherwise, it won't let you reopen a different data set. That's what the clear does. And then there's an import engine that recognizes Excel formatted data. So this $ file save is going to the file save defined up here and inserting that file reference. Make sure your file path doesn't have spaces either. Yes. This is one of the quirky things with Stata. I have seen it work just fine with spaces on some of my computers and not with others. And I have yet to figure out why. But yeah, not having spaces in your file names is one way to make sure that you're streamlining the possible errors. I have seen it work sometimes though. I don't know what the difference is yet. Um, Case preserve is going to keep the names of the variables either lowercase, uppercase, whatever they were. Otherwise, it automatically converts all the variable names to lowercase. This matters because Stata is case sensitive. This drives me nuts, actually, to have to always type in lowercase because the way that I code is that designated commands are uppercase and things that I would change are lowercase, and I can't use that here, which is part of the reason why I always capitalize Stata, just to like make those people mad because it's never capitalized when they do it and I always do it. It's just, I've actually had people try to correct me in written work and I'm like, no, I'm trying to be snarky. You don't understand. I'm taking out my pent up aggression and not being able to have title case or uppercase as I see fit. Weird spaces work for me in Windows 10. Yeah. I honestly don't know, but if you have problems with the file path, check for spaces and take them out if possible. That would be my recommendation. The H drive doesn't seem to have a problem with that because the H drive has like a default like my SAS files in it, and people have used that folder just fine. So who the hell knows? Okay. Label define. This is the same thing as the proc format. It is defining the labeling conventions for your categorical variable values. Labeling the variables themselves, very similar except there's no equal sign and the words label variable have to precede each one. Then applying the labeling conventions of the variable values for categorical variables, so the variable itself and then the convention. To do z-scoring, that is within Stata something called an egen. So when you make new variables in Stata, it's usually going to be one of two things. It's either gen or egen. I think of egen as fancy gen. So like if I try something with gen and it doesn't work, I put the e in front of it and like 9 times out of 10 it will work. So egen is for uses of functions and things that seem to be a bit more complex. That's my best guess as to how to explain that. So egen is an example of this STD is a function. No, it does not give you a venereal disease. It gives you a z-score. Just checking to see if you're all with me. See, that was funny, right? Yes, STD references, hilarious. This is what pandemic humor. This is where we're left with. All right, so this is the standardized version inside, and then gen, which is the regular one to get the log transformed version. So using the built-in log function there. And now their data set is ready to use. All right, so any questions on the Stata code or problems that you've encountered? All right, so anytime that you want to do an analysis, you will have to do something along these lines of importing data and making sure that all of the information that you need attached to the data is there. If you're working with existing data already saved in, say, a Stata format or a SAS format, odds are good that these labels will already be there for you. So you won't have to do all of this, but I wanted to demonstrate how to in the case that you're working with data that haven't been properly formatted and labeled. Okay, so first thing, a little bit of review. So let's get some descriptive statistics. Learn about these variables that we're going to be playing with. So since we have quantitative variables to be talking about in this example, income and education is going to be another one. We can ask for proc means in SAS to get descriptive information. So this statement right here, n decimals, this thing right here, n-des equals 3, that's just controlling how many significant digits it prints after the decimal place. I just do that to make it look a little nicer, but you can pick whatever you'd like. No labels suppresses the labels as an extra column, and the reason I did that is to make this fit on the page. There's no other reason than that. And then this is all the stuff that I'm asking from this, the mean, standard deviation, minimum, and maximum. These headers, this is what you would get by default. So you don't actually have to type all of this to get this information. You can just type the proc means, the data set, the variables that you want to summarize, and then run makes it go. So this data set has 734 cases in it, and then I'm giving you 3 different versions of income: the original, the version that's been z-scored, and the version that's been log transformed. So review question for you. Which of these is different than the others? If I take a variable and z-score it, what kind of transformation is that? Linear or nonlinear? If I take a variable and z-score it, that's linear. So I'm just changing it so that it has a mean of 0 and a standard deviation of 1, or a variance of 1. That's linear. Linear transformations don't change the information otherwise. It's a transformation that's evenly across variables. So the odd man out is log, actually. That's the one that takes positively skewed data and the tail reels it in, and the other side, it takes it and stretches it out. So if I were concerned about the influence of, say, people who make a lot of money on measures of association, log transforming the variable might be one way that I can test whether or not those extreme cases are biasing the results, so to speak. So this is the one that's going to be not like the other two. And then education is being treated as a continuous variable, even though it's not really, because it's in interval years. So I would call this continue-ish. It's years of education. We're going to play a lot with how education predicts income, because one more year of education doesn't mean the same thing. It depends on whether you're talking about another year leading to a degree or just another year on the way to a degree. Here are some more things that you can ask for out of proc means: standard error of the mean and confidence limits. So you'll get a chance to practice this in homework 2. So I'm getting the mean again, and I'm getting the standard error of the mean. So the standard error of the mean for original income, for instance, is 0.5. The standard deviation of income is 13. What's the difference? What's standard deviation of 13 telling me? Data point deviation from the mean on average. Yes. So standard deviation is referring to your one sample and the people in it. On average, a person who's responding to the survey said they make $17,000 a year. That's what the 17 means. But the variability of the sample is such that on average, someone is off from that mean by $13,000. The fact that 13 you can have a bunch of 13s going positive, but only one going negative is indication that the variable is going to be skewed, because you know it can't go below 0. The lowest value is 0.2, and the highest value is the 68,000. So if this describes how far off a person is from the mean, what does standard error give me then? Because it sounds the same, but it's not the same. Same thing, but the data points are means now. Yes, indeed. So a standard error, throughout the semester, you're going to get this question over and over and over. A standard error is how far off the sample version of the statistic is from the population version on average. It's an index of imprecision across repeated samples. So on average, the sample mean would be expected to be off from the population mean by about 0.5. And the confidence interval around this sample mean is computed for me right here. And it's using whatever t is most appropriate given that shows an alpha level, which I've set at 0.05, and the sample size. So it's figuring out what t critical needs to be to make this interval, and it's t critical times the standard error as the part that goes plus or minus around the mean estimate. Same thing with education. On average, people are reporting 13.8 years, but that sample mean would be off from the population mean on average about 0.1. So the fact that this is a relatively large sample is responsible for the fact that these standard errors are pretty small. And here's the confidence interval around that mean. Stata folks, it looks almost exactly the same, except that you have the word summarize that gives this to you. And Stata also decides how many significant digits to print, and it varies across this display. This sort of drives me nuts, I gotta tell you. Like 1, well, it's exactly 1, so I don't need any zeros. But the mean is printed of 0 up to 10 decimal places. So you gotta look at your output a little more carefully because things are not as aligned as they would be in other programs. Here's a new one for you. The procedure just mean in Stata is yet another way to get information about sample means. And in this case, it gives you the mean and a confidence interval by default. Note that we're specifying level 95, asking for a 95% confidence interval. That is the same idea as alpha of 0.05. So 0.05 is the unexpected alpha, 95 is the confidence interval for expected, where those start. And the values that it agrees on are the same. So you'll get a chance to review this material in homework 2, and then we get a chance for some new stuff. So Pearson's correlation. Question, so 95 equals alpha of 0.05, yes. A confidence level of or a confidence interval, basically if you're specifying the expected part, that's 95%. The unexpected part is the alpha level. So the program will ask you for that information from either perspective. It's level in Stata and it's alpha in SAS. So correlations. Very similar structure of asking for things, proc something, data equals the name of the data set, options for what you're asking for, what variables do you want the information for is on the var statement, and then run means thank you. Title. This is me leaving a note to myself that's going to show up in my output. So that's me trying to help figure out what I'm staring at later on. This title that is just all by itself, the role of that is to shut off this title. Otherwise, it will just keep printing over and over again as I run other things, even if it's not relevant. So you don't have to add these things if you don't want to, but it's helpful in terms of making your output easier to digest. Proc core, can you guess what core stands for? Correlation, yeah. I once had a question from a student like, are we expected to just memorize what these procedures are? You're expected to memorize maybe which proc it is if it makes your life easier. But the rest of this, no. Like if you can just remember that correlations are given to me by proc core, means are given to me by proc means, like that's enough because then you can search those terms through your notes or through the Google and find the rest of the options. So don't worry about keeping all of this as part of your formal memory of this process. So proc core gives you correlations of all different kinds. In SAS, so this is an extra step that SAS requires that Stata does not, you need to tell it what data set you're pulling from. So this would be something that you have to change to your homework data. Pearson is an option that gives you Pearson correlations. This is actually a default, but just to illustrate this relative to the next kind that we're going to look at. And then this thing right here, that is an option that is going to do the Fisher R to Z nonlinear transformation by which you can get confidence intervals around your correlation. So it's going to do that fancy formula that computes an unbounded version of your correlation, figures out what the standard error and the boundaries would be for the confidence interval, and then back translates all of that into your correlation metric. Alpha of 0.05, as you might have guessed, means I want a 95% confidence interval. If I changed my mind and I wanted to be stricter, if I wanted to have a 99% confidence interval, what would I change this to? Yeah,
0.01.
0.01. See, watch. Ta-da! You can get whatever you want. Could I get like a 67% confidence interval? Sure. Right? I can just pick whatever I want. It'll do it for you. But 0.05 is the magic number that everyone has decided on, so we'll go with that. This part right here, that bias adjust, that means that it is going to compute the sample size corrected version of R and put the confidence interval around that. So that will not make much of a difference in a sample this large, but it could. So you can choose whether or not you want to adjust for sample size. That would drag your correlation down a little bit by the adjustment. Can you guess if you didn't want the adjustment, what you would type there? Bias adjust equals no. Yeah. So there's a little bit of sass that's in English. Not much, but some. The variables that we are correlating, you can create a list for on the var statement. So var right here means variable. Which columns of the data set do you want me to do this to? And it gives you all possible correlations in a matrix, which is what this piece of output right here has. So this is what's known as a square matrix, and in this case the rows and the columns are exactly the same. So that means half of this is redundant. So what goes on the diagonal is a 1, meaning that each variable, come back, is perfectly correlated with itself. So that's kind of like your reference point for staring at the rest of this. Then 2 values are given for each combination. So for instance, this is the column for income with the row for income z-score right here that I'm looking at. The first number, the top number, is the Pearson correlation estimate, and the second number is the p-value. So this correlation of 1 is just reminding you that z-scoring is a linear transformation. Income is perfectly correlated with the z-scored version of income. It's not distorting the information one bit, it's simply changing the scale. Z-scoring gives you a mean of 0 and a standard deviation of 1. It's typically done to a series of variables that have different metrics so that they all have a comparable unit with which to assess how they relate to other things in models. In contrast, if I stay in this column for income and go down to the next entry, 0.82 is the correlation between income and the natural log transformed version of income. They're not the same, otherwise the correlation would be 1 again. It's a nonlinear transformation. So it's taking extreme positive values and shoving them back closer to the middle of the distribution, and it's taking the smaller ones and kind of spreading them out. That's what it looks like. Under each of these correlations is the p-value. And to know what that means, SAS tries to help. This up here, probability greater than R in bars under HO rho equals 0. Crystal clear? You know some engineer was like, what? I told them what it means. How do you not understand that? Well, if it were that easy, I would not have a job. So that's the good news. There will always be people who want to pay you to figure this shit out for them. So probability greater than R bar. What's R bar mean? The bars around R. Any guesses? Absolute value, yeah. So just re-emphasizing that a negative correlation and a positive correlation of the same number are just as strong as each other. Probability under HO. What's HO? Yeah, null hypothesis, what we expect. And then rho equals 0. Yeah, rho is what the population correlation is supposed to be called. And so this is saying that if our benchmark is that we are seeing if how likely it would be to get what we found if the population correlation were 0. Now we can change that, actually. There is another option possible inside this Fisher statement right here that allows you to gain tests against an alternative null hypothesis. You can say, I want to test against an expected correlation of 0.3, and you can totally do that. You would have to have a reason to pick whatever that is, but it is possible. By the way, in another excellent set of terminology, do you know what it's called if you pick a null hypothesis that is not 0? A non-nil null. Yeah, a non-nil null. Say that 13 times fast. That is what it's called. So, FYI. So this is telling you these values underneath here, which in this case are all less than 0.01, what is the probability of observing a sample correlation as extreme, so positive or negative side, if the true population correlation were 0? And in every case, all of these p-values are less than 0.001, meaning that if there was no association in the population, we would find correlation statistics in a sample as extreme as this, less than 0.01% of the time. Very unlikely. So every correlation in this matrix is significant, is unexpected if the true association were 0. But they're not all the same. So for instance, the correlation between income and education is positive. So we know that as education goes up, income goes, help me out here, audience participation. Yes, up. As education goes up, income goes up. That's what a positive correlation means. But is it guaranteed to go up? No. Yeah, if it were guaranteed, that would be a correlation of 1, right? This just means like likely to. Yeah, ish. Up-ish is the way I would phrase this. A correlation of 0.4. Not super huge, not super small. So the p-values that go with these things, right, they don't tell you any more about the strength of these associations. They're all unexpected. But a correlation of 0.8 is not the same as a correlation of 0.4. And you'll note with the symmetry of the table, so like if I look at this number right here, the correlation of income with log transformed income, that same number shows up over here. So the off diagonals are symmetric, which means that you only have to pay attention to the lower triangle of this thing or the upper triangle. And when you report correlation matrices in publications, they'll often only do half of it because the other half is redundant. If you have more than one group to report, sometimes they'll put group 1 below the diagonal and group 2 above the diagonal or something like that to save space. But otherwise, this matrix has twice as many correlations in it as you actually have estimated in the data. Okay, how are we doing? So this tells you a correlation estimate for your sample. Where's your test statistic? Do you see anything that's labeled T? Nope. So SAS just skips over that step. It doesn't give you the t-test statistic. It goes straight to the p-value that would be generated from your t-test statistic. So when you're reporting these things, such as in a results section forthcoming, like right here. So I'm going to keep doing this for you in all of your handouts. Words. My gift to you, free words, your tuition dollars at work. Because it does you no good to know how to run this stuff if you don't know how to tell somebody about it. So this is an example of what it would look like to write a results section for a manuscript or a dissertation, what have you, publication purposes, that would summarize these correlation type analyses. So you would usually, if you haven't already done so, describe the variables in question, so their mean, standard deviation, and ranges. And then in terms of describing the results, the correlation estimate and the p-value that goes with it. Correlation is your effect size for how strong the association is. P-value is your significance test reporting. Basically, if against a null hypothesis of 0, a correlation as big as 0.385 would be found less than 0.01% of the time. The extra part that goes with the confidence interval here is what we're going to get to next. But the most important part of any results section is to translate this into English. That is the most important part. You got to give the people the part they're going to highlight, right? Because no one's going to highlight this as the thing they want to remember. So in all results sections, it's like, we found stat, 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 comma, indicating that, or such that. I like indicating that a lot, but that is the most important part. So after all of that is said and done, we have the pattern indicating that greater education is associated with greater income. Note the wording here. I'm just saying these things are related. I'm not saying that if you have more education, that's going to cause you to have greater income or vice versa. They are associated in a data set. We'll talk a little bit about that next week or the week after in terms of causal attribution. Basically, you don't have any unless your design supports it. And that's rarely the case in a lot of data sets. So if we just have this observational data, we can talk about associations. And then I have an extra piece here that I probably wouldn't include for publication purposes, but just for you guys in terms of what the p-value actually means. A sample correlation more extreme than what was found would be expected less than 0.01% of the time if the population correlation were actually 0. If the population correlation were actually 0 is the important part. That's your benchmark for establishing probability. Okay, let me scroll back up here. All right, and we're already out of time. Goodness, time flies when you're having fun. Well, I'll leave you with this pretty picture. Office hours start at 3:15 if anyone wants to come chat with me. Otherwise, I'll see you next time. Stay safe, stay sane. See you Thursday.